And when you watch it happen, it's actually really silly to a guy like me. You take all these stamp panels, you put them together, then you put them in a framing station, you build a body that looks something like a car, you put the doors on, and then you paint them. Once you get the color, you take the doors off, and then you start putting the interior inside the car. It comes in through the openings that already exist. I wish it went in like this big piece like this, but there's actually people coming in and out of the car. There's awkward movements. Then we lift the car up. We put stuff from underneath it. We put it down. Then we put the seats in the car. And finally, we close it all out with glass, and we bring those doors that went away for a trip, and we put them back in the car. Most of the time, we're doing this with a big, giant car and moving it and doing really nothing to it at all.
What's funny, though, in this kind of whole process is that just recently Toyota just called this an engineering work of art.
True.
The Model Y.
That was humbling, but at Tesla, it's not good enough. If we're going to scale the way we want to do, we have to rethink manufacturing again. As part of the master plan, we have to make another step change in cost. We started this on Model Y when we made these huge gigacastings. And we deleted hundreds of parts. We simplified assembly with the Model Y structural battery, where we decided the floor should be a part of the car. The battery is the floor. We put the seats in the interior on the battery, and we bring it up through a big open hole, and we assemble it. And this allowed us to do things in parallel, fully rethinking the process and reducing the final assembly line by about 10%. And we thought, maybe we could do this other places.
Yeah, I mean, in a way, the constraints become part of the solution rather than a problem.
So when you think about what I'm trying to say, I really want to hammer this home. When you have a car that's about 5 meters long, and you have people working around it like we did in Model 3, and we change that to this process where we take different parts of the car, and we can do more at the same time, like we did with the Model Y structural battery pack. What you see here is us doing that on the front part of the vehicle, or the rear part of the vehicle. That means we can get more people working on the car, or robots, working on it at the same time. That means we have better operator density, less time doing nothing. I call that space-time efficiency. It has nothing to do with quantum mechanics. We can have that conversation later. But we get 44% more operator density, which means more work, less time walking back to the station, 30% improvement in space-time efficiency. And because we're not building it in and out of the car with those slow movements of those robots I showed you from production hell, when we go to automate it, it's going to be a lot easier. In the end, that will probably look something like this, where we balance parallel and series manufacturing in a way where we only do things that are necessary, with a much shorter final line, blocking a lot less of the entire rest of the factory, so we can optimize material flow using the best practices. And what that means, it's going to look something like this, where we build all the sides of the cars independently. We only paint what we need to. And then we assemble the parts of the car once and only once. We put them where they need to go. The interior is attached from a bottom-up or a top-down strategy, so there's more access for those robots and people. We aren't moving heavy objects around and doing nothing to it. And it means we're doing more work on the car more of the time. And then when we take all of these tested sub-assemblies and we put them together, we finally assemble the car only one time, putting the sides on with all of their parts to a front and rear that was already assembled, carrying the floor in with the seats, and finally boxing it out with the doors one time, just like Cybertruck. So in the end, you get the same car, but it's not going to be a Model Y.
Yeah, this is not. Yeah. This is a Model Y for illustration, not the next-gen vehicle.
In the end, what does that mean? To increase the scale and adoption of electric vehicles on the orders of magnitude that we just showed you, we have to make constraints part of the solution. It leads us to greater than 40% reduction in footprint, which means we can build factories faster, with less CapEx, and more output per unit. Faster, less CapEx, more output per unit dollar.
In our next powertrain, so those silicon carbide transistors that I mentioned that are key component but expensive, we figured out a way to use 75% less without compromising the performance or the efficiency of the car. And of course, we know that battery cell supply is one of the constraints on the scalability of EVs right now. Our new powertrain It's compatible with any battery chemistry. And that will give us great flexibility in battery sourcing. If we want to make EVs more accessible to people, they have to be cheaper. We've reduced the drive unit cost to about $1,000, and we don't think any other automaker is even close to that number. Finally, the bigger a factory is, the longer it takes to build. If we can build the same number of cars from a smaller factory, we are going to be able to scale EV production faster. Our next powertrain factory is 50% smaller than the one that's behind me today, even though it has the same capacity. All of these improvements, I think, are going to be transformative for the adoption of EVs and our ability to scale them. There's one more thing that I want to highlight. So I talked about how we had reduced the amount of rare earth in our powertrains. And as the world transitions to clean energy, the demand for rare earth is really increasing dramatically. And not only is it going to be a little hard to meet that demand, but mining that rare earth, it has environmental and health risks. So we want to do even better than this. We have designed our next drive unit, which uses a permanent magnet motor, to not use any rare earth materials at all. So how does all this fit into the master plan? We can make lower cost products that are still efficient and compelling, and we can make them at scale. We're going to use less of constrained commodities, silicon carbide, rare earths. We're going to build them all in compact and high output factories that are easy for us to build quickly. We're going to make that easy to scale powertrains all the way up to the levels that Drew and Elon mentioned at the beginning. And this achievement, like all of the achievements that I mentioned today, it's only possible because of the incredible people on our powertrain teams. They are absolutely committed to the cause of sustainable energy, and that is why we can do what no other company can do. Thank you. So next, I'd like to welcome my colleagues Pete Bannon and David Lau.
Thanks, Colin. Good afternoon, everybody, and welcome to Texas. Pictured here is the low-voltage system of a Model S from 2012. This car was primarily designed with vendor-sourced controllers integrated by Tesla. There are over 300 low-voltage devices that encompass everything from the mundane, like the light in the glove box, to the complicated, like the infotainment computer, to the safety-critical, like the airbags, steer-by-wire, and brake-by-wire. The low-voltage harness is built from individual wires, cut to length, crimped, and inserted into connectors, a manual process that is tedious, error-prone, and doesn't scale well. Going forward, we want to reduce the size and complexity of the harness and enable automated manufacturing.
These wire harnesses introduce extraordinary complications, especially in the early stages of development and bring up of a vehicle, because when we're trying to bring up this entire system and we see that it's not working properly, we don't know whether it's a problem with the software, with the controller, the processor, any of the endpoints in this entanglement of wires. And so we have to go and debug everything all at once. And Pete's going to tell us about how we're going to make it better.
Mm-hmm. So I'm going to talk briefly about a few things that we've changed over the years since the Model S. With the Model 3, Tesla started designing an increasing share of our controllers by merging controllers together, and we were able to simplify the design with a significant reduction in wire count and weight. Going from S to 3, we reduced the wire harness by 17 kilograms compared to Model S. And this is a pretty big deal. And just to put that into context, our VP of Engineering, Lars, will deliver a bottle of your favorite spirit to your desk if you manage to save a kilogram of weight from the car. So this improvement cost him quite a lot. Did we skip one? Yeah. The original Model 3 controllers were enhanced and then built into Model Y. Those improved controllers were then moved back into Model 3 when we introduced the heat pump. At that point, we had shared controllers across both cars, which helped simplify our supply chain. Those Model 3 and Y controller designs were then updated and enhanced for the new versions of Model S and X that we introduced in 2021. For Cybertruck, we are now designing 85% of the controllers in the car. For the next-gen platform, we're going to finish the job and be designing 100% of the controllers to give us full control of the design and the supply chain at the component level. Having full control of the supply chain at the component level has been critical to Tesla over the last few years as the supply constraints have hampered our ability to build cars.
And with that control comes control over all the software, which enables us to develop features and functionality that we never even dreamed of at the time we designed the hardware. So that's why you see software in your cars getting better and better over time in ways that we didn't even think of when we designed the hardware in the first place.
Yeah, Sentry Mode is one of my favorite last-minute changes.
One of my favorites.
With the introduction of Model 3 in 2017, we deleted relays and fuses from the car in favor of e-fuses. E-fuses replace moving parts with solid-state transistors. They provide fine-grained control of the power system to software and allow software to do advanced things like load shedding in the car under adverse conditions. E-fuses also allow for software-controlled retries for transient faults, and they allow for detailed monitoring of the power system over time.
Yeah, the theme you hear a lot about today is software-controlled hardware. And when I think about that in my team, software-controlled hardware is fundamentally about being able to sidestep what otherwise would have been static trade-offs between one attribute or another in a piece of hardware. We are able, with software, to instill intelligence, context awareness, and context-specific behavior into what otherwise would have been a piece of hardware that had to get optimized for one type of scenario. We get more of everything.
In 2022, we completed the transition from lead-acid batteries to lithium-ion batteries, and which use a new toolless connector. We expect lithium-ion batteries to last for the life of the car, so we don't expect anyone to wake up to a dead battery ever again. This eliminates a major source of failures for our car. And the toolless connector makes it easier to service the car, and it also includes a software feature to allow validation that the connector has been properly installed at the end of a service event, which removes another source of failures in our cars. Obviously, the mass and volume savings are also significant, which is super helpful. At Tesla, we're always trying to improve every single component in the car, and a nice example of that is the 15-inch display that was originally shipped in the 2017 Model 3. Over time, the cost of the display has gone down 24%. We've been able to reduce the weight by 12%, and we've reduced the power by 33%. At the same time, we've increased the brightness of the display by 50% and improved the color accuracy. So this is one of our favorite things at Tesla, is to make a component cheaper and better. At Tesla, the drive to improve efficiency in the car is never ending. I think of it as like peeling a carrot. You just take a swipe at it, a little bit falls off, doesn't really make much of a difference. But if you just keep at it, over time it accumulates into a pretty significant improvement. One of the changes that we're looking to make right now is to change something that's been steady for the last 60 years, 12 volts. 12 volts has been, as I said, for 60 years. The demand for power in the car has been steadily increasing to the point where we now have to have pretty large wires to drive over 200 amps of current around the car, which increases the mass and cost. With Cybertruck and all future Tesla platforms, we will be moving to 48 volts. This reduces the current needed by a factor of 4. And since power loss in the harness is resistance times the square of the current, a 4x reduction in current leads to a 16x reduction in lost power while distributing energy in the car. That allows for smaller wires, smaller e-fuses, and smaller controllers. It also allows us to make those heat sinks smaller, or in many cases, remove it completely, all benefiting the car in terms of mass and weight. 48 volts is the future for low voltage design at Tesla, and likely the rest of the industry in due course.
We welcome and encourage other OEMs and the entire supplier network to join us on this evolution.
You bet. The number of wires in the car is driven by the number of endpoints that need to be powered and controlled. In the past, centralized control has led for wires spanning the entire car. For Cybertruck design, we have moved to a local controller where the wire is connected to the nearest controller, and those controllers are connected over Ethernet. Wires are routed to the nearest controller where the data is converted into a network packet for transmission to the correct location in the car. To be effective, the network must be reliable, have low latency, and low jitter, and these are all attributes that we've been able to achieve with the current design. The design has eliminated most of the cross-car wires in Cybertruck, and with the next-gen platform, we're going to finish the job and eliminate all of them.
This consolidated vehicle network allows us also to make a whole lot more dynamic changes on the fly to how components in the vehicle talk to each other, rather than the traditional approach of separate CAN buses that are spread throughout the vehicle and fixed in hardware.
And one of the nice things is that you can see the entire vehicle through a single connection, which wasn't possible in the past for debug. For the next-gen platform, we're looking to optimize the controller design across the entire car and across all of the organizations, not just for a given subsystem. Simplifying the wire harness will enable automation. 48 volts will allow us to reduce the size, mass, and cost of the low-voltage system. And it's one of the key things to enabling us to scale production of the low-voltage systems for the Master Plan 3. David?